Most people assume that the durability, lightness, and versatility of modern plastics have always been available to engineers, manufacturers, and the military. That's a misconception. In reality, before the 1950s, materials engineers faced a series of constraints that demanded both creativity and pragmatism. During conflicts like World War II and the Korean War, shortages of metals, rubber, and synthetics forced engineers to rely on materials that were entirely organic, mineral-based, or early synthetic analogues. These choices often determined whether equipment lasted in the field, whether supplies could be moved efficiently, or whether soldiers could survive harsh conditions. For viewers who want a deeper understanding of the ingenuity behind wartime engineering, subscribe now to History Matters. We'll explore how materials that seem archaic today were once cutting-edge solutions to life-and-death problems. During the early 20th century, especially in the 1930s and 1940s, demand for steel, aluminum, and copper skyrocketed. Armies required vehicles, weapons, and communication equipment in unprecedented quantities, while industrial expansion consumed metals for civilian infrastructure. Engineers had to find substitutes for applications where metals were scarce. Wood became a structural material not just for shelters, but for aircraft components, boat hulls, and even anti-tank obstacles. Laminated wood techniques allowed planes like the de Havilland Mosquito to achieve remarkable strength-to-weight ratios. In parallel, fabrics, canvas, and treated leathers were adapted for everything from storage containers to flotation devices. The lessons here are clear: resource scarcity drives innovation, and understanding material properties is essential when conventional solutions are unavailable. Synthetic rubber existed in rudimentary forms by the 1930s, but supply chains were limited and often disrupted by wartime events. Tires, gaskets, and hoses relied on both natural and synthetic rubber substitutes. Para rubber, guayule extracts, and even modified gutta percha were experimented with in military applications. Engineers needed to account for tensile strength, elasticity, and temperature sensitivity. A hose that worked in temperate Europe might crack under Arctic conditions or become sticky in the tropics. These material limitations forced careful testing and iterative design, long before modern polymers provided predictable performance. In practice, engineers learned to combine multiple materials, layering rubber with canvas or impregnating fabrics with resins to create composite solutions that could withstand varied conditions. Bakelite and phenolic resins represented a turning point. Invented in the early 20th century, these materials allowed for hard, heat-resistant, and electrically insulating components. Telephones, radio casings, and weapon grips were made from these plastics, long before polyethylene or polypropylene became available. The real innovation wasn't just in creating a new material, it was in identifying the right applications. Engineers had to understand thermal expansion, brittleness, and chemical resistance. A phenolic grip on a rifle, for example, needed to resist sweat solvents and repeated stress. This knowledge informed later polymer development and even modern composite engineering. What seems mundane today, plastic-coated wires, molded handles, or lightweight housings, was once the product of meticulous material experimentation. One overlooked aspect of pre-plastic engineering was the use of coatings to compensate for material weaknesses. Metals were often painted with early anti-corrosive coatings or lacquered to prevent rust. Wood was treated with oils, shellac, or waxes to resist moisture and termites. Fabrics were impregnated with linseed oil or other varnishes to improve durability. These treatments required precise ratios and application techniques. Too little and the substrate would fail, too much and the coating would crack or peel. Engineers and technicians quickly learned that protective coatings could extend functional lifespan by years, often with minimal weight or cost impact. The principle is simple yet profound. A material's performance is not determined solely by its base properties, but by how it interacts with its environment and treatments. In both the European and Pacific theatres, soldiers and engineers were forced to improvise with what was available. Wooden crates were reinforced with metal strapping or resin coatings to transport ammunition safely. Canvas tarps were, layered and waxed to store fuel or protect communications equipment. Early plastics and resins were sometimes molded right there in the field to replace broken parts. These improvised solutions were not inferior. They were often essential. Supplies would otherwise degrade, vehicles would fail, and operations could, stall. The lesson here is that understanding material limitations and potential substitutions can be the difference between operational continuity and mission failure. Modern survivalists or engineers studying these examples can really see how practical ingenuity often outweighed technical superiority. Aircraft construction provides some of the clearest examples. The de Havilland Mosquito, famously known as the wooden wonder, combined balsa, plywood and caisson glue to achieve high performance. Steel shortages and, the need for lightweight speed made this combination far superior to conventional metal designs in certain roles. In naval applications, wooden minesweepers and auxiliary vessels relied on carefully treated wood and early plastics to minimize magnetic signatures. Communications equipment, including field radios, used bakelite housings, treated cords and canvas straps to survive both weather and handling in frontline conditions. Even simple items like water bottles were constructed from coated metals or laminated wood composites when aluminum or early plastics were unavailable. The improvisation and experimentation of wartime engineers laid the foundation for modern materials science. Many synthetic plastics, composite woods and resin formulations were refined from lessons learned in field conditions. After the war, laboratories really shifted their focus to scaling these materials for civilian use, which led to the creation of more durable housings, furniture, and insulation. Field experience showed just how important it was to test materials under real-world conditions. This actually led to the development of standards for stress temperature and chemical resistance, standards that, interestingly, still persist to this day. By studying these historical materials, engineers gain valuable insight into problem-solving under constraints. Honestly, that's an invaluable lesson for anyone interested in design, survival, or even just logistical efficiency. The story of pre-plastic materials is not simply about chemistry or engineering. It's really about human ingenuity in the face of scarcity and challenge. These innovations, they influenced outcomes on the battlefield, helped infrastructure survive in harsh environments, and ultimately shaped the entire trajectory of modern materials science. For historians, engineers, and survivalists alike, understanding the properties, limitations, and potential of materials used before plastics gives, a fuller picture of how innovation occurs under constraint. It reminds us that many of the conveniences we take for granted today were actually built on decades of trial, error, and practical experimentation. For those interested in the intersection of history and survival, these examples provide more than just historical curiosity. They offer actionable insight, really. Studying pre-plastic materials teaches adaptability, resourcefulness, and the value of understanding properties and limitations. For modern makers, engineers, or off-grid survivalists, techniques such as combining treated wood with natural resins, using coatings to extend lifespan, or layering materials for strength are, honestly, directly applicable. If you value digging beyond superficial history and understanding how real innovation happens under pressure, subscribe to History Matters. Share this video with anyone interested in the ingenuity that shaped both past conflicts and modern materials. By studying what came before plastics, we gain perspective on the importance of adaptation, resource management, and thoughtful engineering. Lessons that remain vital whether on the battlefield, in the workshop, or in our everyday lives.